Hello everyone. So in this video, we are going to see one particular topic that is related to induction motor. Okay. In induction motor, we are going to see if we change the voltage, supply voltage, what will be the impact of the impact on the induction motor torque slip characteristics, and how basically the changing voltage are going to impact on the induction motor performance. Same thing we will check if we change the supply frequency, what will be the impact on induction motor performance? And also there will be another case, that is variable voltage, variable frequency. Like voltage and frequency we will vary and we will keep the VYF ratio constant. In that case, we will study what will be the impact on the induction motor performance. Okay. So what are the cases? So first I will consider case number one. My frequency is constant, supply frequency is constant, and my supply voltage is varying. Okay, so this is my supply voltage, let's say. And second case, my frequency is varying and my voltage is constant. Okay, and third is V by F ratio is constant. Okay, I'll be changing voltage and frequency to keep this ratio constant. So these are the three cases we will study. And before I proceed, maybe it will be good to know the some of the equations and all, because the rest of the analysis that will be depends on some kind of mathematical analysis and all. Okay. So in my case, what I am doing, let's say I am assuming the stator leakage and reactance are zero, and even I'm not even considering the, you can say, the core loss resistances and all. Generally, if you see the per phase equivalent circuit diagram of induction motor, it is something like this, refer to primary actually. In case of induction motor, you cannot actually neglect this xm basically, because uh, in induction motor at no load, it draws around 30 to 40% of full load current. Okay, so you cannot neglect the xm. Here you have R2, here you have jx2, and R2 1 minus S by S. So this is the per phase equivalent circuit diagram of induction motor. Okay, so in my case, I am assuming this portion, like this portion uh, is zero. So I'm neglecting these things. Okay, so let me neglect it. Just for simplicity, I was just wanted to have a simple equations, and you can also represent this particular circuit as like this. Okay, now let me start with what do you say, to writing the equations and all. I wanted to calculate what is the developed electromagnetic torque. I want to calculate what is developed electromagnetic torque, TD. Okay, so from this particular circuit, let's say your rotor current is I2. So what will be your developed power? PD is equals to, it is a three phase, so 3 will come, I2 square into R2 1 minus S by S. This is your developed electromagnetic power. Okay, because this part is representing the mechanical load in electrical domain. You can say you are representing the mechanical load in electrical domain as a heat loss component, so it will be that mechanical load, you can say. So if I write that, what is my developed power, 3 I2 square R2 1 minus S by S and I2 is nothing but Vs uh, R2 by S plus J x2. Okay, so this is the thing. So if I take magnitude of this I2, Vs square R2 by S whole square plus x2 square. So put into this equation PD, developed power Vs square plus x2 square into R2 into 1 minus S by S. Okay. Now developed torque will be, see, developed power is equals to developed torque into omega R. So your developed torque will be PD by omega R, and PD you have, and omega R is nothing but omega S 1 minus it. So put this into that equation. So you will get 3 by omega S into Bs square R2 by S R2 by S whole square. See, this Vs is nothing but the supply per phase voltage. Okay, per phase voltage, that is from coming from the supply. Okay, so it is a per phase voltage. Vs is equals to V per phase. So maybe I can write V per phase now onwards. Okay. Now let me write it again. Tt is equals to 3 by omega S into V per phase R2 by S R2 by S whole square plus x2 square. Now, basically in induction motor, at steady state in general, the sleep is near to close to zero actually. And in induction motor, you have basically two operating zones, you can say. If you see the induction motor torque slip characteristics, this is how your torque slip characteristics look like, and this is your slip at maximum torque. Here you have the developed electromagnetic torque. Here you have the speed omega r, and here you have the synchronous speed omega s, and slip is increasing in this direction. Okay, here you have slip maximum, and here you have slip zero. Basically slip is zero. Okay, so this is how your characteristics look like, and this particular area is something we call the operating area of induction motor. In this particular area we call it as a low slip region. Why? Because here the slip is very less, and if you, let's say, from these equations, at low slip region I want to approximate the generator electromagnetic torque at low slip region. I can say my R2 by S, this quantity, it's much higher than the X2 quantity. Okay, because as my S is close to zero, so R2 by S quantity will be higher. Okay, so put that approximation into the equation. Td is equals to 3 by omega S into Vps square R2 by S, and so that x2 square will be just neglected. So we will get Td is equals to 3 by omega S into uh, S V phase square by R2. Okay, so from this particular equation, you can see Td is directly proportional to slip at low slip region, and you can also see this particular area is somewhat linear. Okay, somewhat linear. It is not linear, actual linear, but it is somewhat linear. So these equations also you have to keep in your mind, equation number 2. Okay, now let me add few more things. This particular torque we call as a starting torque, and this is the maximum electromagnetic torque. So I'm calling TE max, and this is the sleep at maximum torque. Okay, so these are the things we need to check. And now let's say at high sleep region, what will happen? High sleep region. High sleep region, your sleep is close to 1. Okay, what you had for the developed electromagnetic torque, 3 by omega s v phase square r2 by s r2 by s whole square plus x2 square. Now as your sleep is close to 1, your r2 by s is much less than x2. You can just assume like that way. Okay, so td is equals to 3 by omega s into v phase square r2 by s x2 square. So here you can see your td is inversely proportional to sleep, you can say, or so it will be like kind of parabolic in nature. Now this particular equation is valid for high sleep region, and your high sleep region is basically this particular zone, you can say the starting zones and all. And also at starting, your sleep is at starting, your sleep is 1. So you calculate the starting torque, T starting 3 by omega s, put s is equals to 1 r2 by x2 square. So this is your another equations for calculating starting torque. And also you know the sleep at maximum torque. Sleep at maximum torque is nothing but r2 by x2. So you have to remember these equations. You can say this is required for analysis. Okay, even if you cannot remember it, but you can derive the equations the way I have derived. Okay, so these are the things you have to keep in mind. Basically, whenever we will be changing the voltage and frequency, we will change what will be the impact of those changes in starting torque generation, maximum torque generation, sleep at maximum torque, operating sleeps. In all those cases, we will analyze. Even there are few more equations, and let me derive that too. We will also analyze what will be the impact on the starting current or the total current if there is any change in voltage and voltage and frequency. So basically, from this particular figure, the power here from this point, if you see this power is basically, we call it as a air gap power. Okay, and that air gap power here also, from here also you can see the same, both of the figure are same. So here the power that is coming to rotor circuit is called air gap power, and that PG power will be lost across R2 by S. So let me write down the air gap power equation. PG is equals to 3 uh, I2 square into R2 by S. Okay, and this is also equals to E2 I2 cos theta 2. What is this? So let me explain you. This is my XM. The voltage across this XM referred to primary or referred to stator side. It is nothing but E2, and here you have R2 by S JX2, and you have this current I2, and the power factor angle of this particular circuit is theta 2. So you can write V2 I2 into cos theta 2. This is your air gap power. Can you write? Definitely you can write E2 I2 cos theta 2. Okay, now what will be the developed torque? TD is equals to PG by omega S. So E2 I2 cos theta 2 by omega S. Omega S, okay. And here your E2 and supply voltage both are same. Here you have supply voltage, both are same. And also this is equals to root 2 pi f flux, flux per pole, and number of turns per phase, and kW. So let me write it just flux phi, although it is a flux per pole, just for simplicity I'm just considering only phi. If you see this particular equation, your phi your phi is directly proportional to Vs by F, or you can say E2 by F. Okay. So in place of E2 also, you can write E2 is equals to K phi F. You can write this also. Okay. So you can write TD is equals to K phi F I2 cos theta 2 by omega s. Okay. K is constant and omega is also constant. Uh, and you can write k by omega as another constant, but we will see what can be done. But these are the thing, these equations, and this equation is also important to comment on the rotor current, what will happen in the rotor currents and all. So let me consider first the case number one, uh, when my frequency is constant and my voltage is varying. Okay. So we will see impact on starting torque, we will see impact on the maximum torque, we will see sleep at maximum torque, we will see impact on rotor current I2, and we will see impact on rotor power factor cos theta 2. Okay, so these are the things that we need to analyze from this uh, uh, particular video. Okay, so uh, no uh, what was the starting torque equation? Let me write all of them here. TST is equals to 3 by omega s V phase square R2 by X2 square. Okay, and okay, we need to also calculate the Tmax values, the electromagnetic maximum torque. That we did not even calculate. So here I can calculate the electromagnetic torque max. See from the equation number one. From the equation number one, let me put SMT. We know SMT is equals to R2 by X2. Okay, so R2 by X, I can write X2 is equal to R2 by SMT. We can write, definitely we can write it. So TD is equals to 3 by omega s into V phase square X2 2x2 square. So it is your maximum torque. So TE max 3 by omega s x2. So this is your one more equation. So it is 3 by omega s 3 by omega s Vp square by 2x2. Okay, and sleep at maximum torque R2 by x2, and uh, the torque, the developed torque can also be written as E2 I2 cos theta 2. Okay, now let's say uh, initially that the torque characteristics of the induction motor of any slip or any voltage it was like this. It was like this. And let's say for this particular torque slip characteristics, I had initially the voltage as per phase voltage as V1. Okay. And this was my slip at maximum torque. This was my torque, and this was my the synchronous speed. And also assume my load torque was constant. So my load torque was somewhere here. Let's say this is my load torque, and at a steady state, this was my operating slip. Okay, this was my operating slip. Now what happened? I just reduce the voltage. Okay, if I reduce the voltage, what will happen? We have to see. See, you cannot increase the voltage because of insulation barrier. So you have to reduce the voltage. If you reduce the voltage from this starting torque equation, you can see if you reduce the voltage, it is actually starting torque is proportional to V per phase square. So if you reduce it, so there will be double reduction, you can say. So if initially your starting torque was this much, there will be much more reduction. So maybe this time the starting torque will start from here. Okay, so definitely there is a starting torque minimization. And here in this particular equation, for the maximum torque generation also, you can see if you reduce the voltage, the maximum torque generation will also reduce. Maybe it will be here. And slip at maximum torque, there is no effect. So your torque slip characteristics, see, your torque slip characteristics will be like this. And this particular case, your voltage is V2 and your V2 is less than V1. You can see now at steady state your operating slip is this here. So initially this was your S1, the operating slip. Now you have the slip as S2, and S2 is greater than S1. Okay, what is the conclusion right now? Conclusion is you got more slip. Slip is more, that means the relative speed in between stator rotating magnetic field and rotor is rotor. That is the relative motion in between rotor conductor and rotating magnetic field are more this time. So you have more induced voltage, and you once you have more induced voltage, that means you have more rotor current. So that will lead to more rotor current, and more rotor current means that will lead to more stator current also, and this will increase the copper losses in the stator side and rotor side. So this increase in the copper loss will reduce the machine efficiency, and it will also create excess amount of heat in the machine. So definitely it is something that we don't want. I hope it is clear like how the sleep will increase and how the rotor current, stator current and all will increase, and it will increase the losses into the system. Okay. Now from another, let's say we want to see from this particular equation, we want to utilize this particular equation to understand what will happen. So I have this TD is equals to E2 I2 cos theta 2, and cos theta 2 is nothing but R2 by S whole square plus X2. You can write the impedance triangle for the rotor circuit. You will get this particular equation, R2 square plus Sx2 square. Okay. Now you have what you have done. From this particular figure, you can see your sleep got increased. If your sleep got increased, your denominator got increased. That means your rotor power factor, the power factor cos theta 2, this particular term has reduced. Okay. And also you reduce the supply voltage, that is V2 less than V1. So you have reduced the E2 also. You have reduced this quantity. Now, and at a steady state, your load torque is constant. So your TD and TL must be constant at a steady state. So to make this particular thing constant, your I2 must be tremendously high. Is it clear? So from this particular equation also, you can see your I2 rotor current, rotor current and all will increase, and it will lead to more losses, and it will reduce the efficiency. I hope it is clear. Now let me take the another scenario. Uh, Maybe I can add one more slide. Yeah, here we will discuss the case number 2. Your frequency is varying and voltage is constant. Okay, maybe I can use this, but these equations in my next analysis. Let's say, yeah, these are the things that I need for this particular analysis. Let's say, what will happen? See, from the, let's say initially you had your torque slip characteristics because of any kind of any slip and all, any frequency. Okay, now what you have done, you have increased the frequency. You have increased the frequency. Let this time f2, and f2 is more than f1, and this particular graph is for f1 frequency, and this is your omega s1. Okay, now for this starting torque, what will happen? If you increase the frequency, your x2 will increase, and you can see t starting is inversely proportional to x2 square, because x is directly proportional frequency. So your starting torque, there will be much more reduction. Your starting torque maybe this much this time. What will be the slip at maximum torque? If you increase the this denominator part, the slip at maximum torque will decrease. So initially, let's say your slip at maximum torque here, maybe this time your slip at maximum torque will lie here. Okay, and what will the impact on maximum torque? As you increase the frequency, this time will increase, and simply your maximum torque will also decrease. So maybe this time your car will cross from this point, so it will be this. And as you have increased the frequency, your omega, the synchronous speed at omega s2 will also increase. So your omega s2 also increase. And let's say you had the constant load torque, constant load torque. The one the important thing is, this time you have reduction in the electromagnetic maximum torque also, and there is reduction in starting torque. From this particular figure, you cannot comment on the what has happened to the slip and all, but we can we comment on that? Let's see. Let's see what will happen in the rotor power factor. Your rotor power factor cos theta 2 is equals to R2 by R2 square plus sx2 square. So yeah, from this particular figure, you're not sure what will happen to slip, so you cannot comment on the rotor power factor. But the thing is, you have that less electromagnetic torque and less starting torque, which is obviously it is not even desirable, because your load, like let's say you had this load, constant load torque, and it was like this time. See, let's see, if you do a black start, your motor will not be able to start. Load torque is more than the generator starting electromagnetic torque, so the motor will not be able to start. So like it will it will be in like stationary condition, and the motor will try to draw a huge current. Okay, now let me consider the third condition, where I will be considering the V by F ratio constant. And also let me take the help of these equations. See, if you see the starting torque, if you see the starting torque, mm, starting torque 3 by omega s into V phase by x2 whole square into R2. This omega is proportional to frequency, correct? This omega is proportional to frequency, and as your V by F ratio constant, so your V by x2 also will be constant because x is directly proportional to frequency. So you can see your TST starting torque will be inversely proportional to frequency. So if you are decreasing frequency, your starting torque will increase. So that will be impact on starting torque. Now what will be the impact on sleep at maximum torque? So sleep at maximum torque, if you are decreasing the frequency, the x2 will also decrease and sleep will increase this time. Okay. Now what will happen to the maximum torque? Maximum torque will be constant this time. How it will be constant? Because 3 into, let's say, B phase square into omega s into 2x2. So this is the things, and omega is proportional to frequency and x is also proportional to frequency. So that means the V 3 by 2, you are having V phase omega s x2. This particular thing is giving k times of frequency square, because omega s is directly proportional to frequency and x is directly proportional to frequency. So your v by v square by f square term is also constant. So this will be constant. Okay, so we'll draw the electromagnetic torque. So let's say initially this was your torque slip characteristics for any v by and f. For say, let's say it was for V1 and F1. Now I have reduced V1 and F1 to. We have seen the maximum electromagnetic torque will be constant, but as we decrease the frequency and voltage, the sleep at maximum torque will increase. Okay, and let's say this was the what do you say? This was the omega s1, and this will be my omega s2. As frequency is decreased, my synchronous speed will also decrease. Okay, so my decrease and my maximum torque will increase. Okay, so my maximum torque will increase, sorry, starting torque will increase. So your curve will be like, can say your curve will be like this. So you can see there is a much increment in the starting torque this time. So this is very good for us. Without even changing the maximum torque, you could able to increase the starting torque. So this particular VYF, variable voltage variable frequency drive, is required for squirrel cage induction motor, where you cannot put additional extra resistance to increase the starting torque. Rather, you can do this VYF ratio constant my technique to get the more starting torque. Uh, so it will be very much beneficial for us. Okay, and let's say, can you comment on the load or the power factors and all? Let's say you are driving the constant constant load torque. You have the sleep here now, and you have the sleep again. You cannot even comment from this particular figure, but it has been observed, like in case of this VYF ratio constant method, your starting torque will increase, your maximum torque will be same, and your power factor, rotor power factor will be improved this time actually. So it is a basically, you can, if you take one example for this particular questions, you will get to know like your rotor power factor will increase. Although from this particular figure it is not clear, but actually it happens in practical life. The rotor power factor will increase, and if the rotor power factor increase, that means you can say from that particular equation, TD is equals to E2 I2 cos theta 2. Okay, and E2 is basically proportional to phi and f. Okay, Sorry, the phi is directly proportional to E2 by F. So you can write E2 is equals to phi F, or what can we mention here? Uh, mm, Okay, if you don't even put the E2, E2 is equals to it is proportional to E2 is equals to K times of phi into F. Your this rotor power factor angle, this rotor power factor will increase, and this time your the rotor current will also decrease. Okay, so this is the one advantage you can say. So these are the observations you can get from this particular analysis. But still, if you have any doubt regarding this analysis and all, you can ask me in the chat. Thank you.